Hello and welcome to this edition of Tech Talk. This is where we bring technical experts from Cisco to share their insights on specific topics selectively chosen based on most common conversation themes on our technology area in community. It's an effort to share valuable insights from Cisco experts on those popular themes. We hope you like it. My name is Satish Chandran and I'm the community manager at Cisco, and today our topic for discussion will be troubleshooting high CPU due to multicast. Our expert joining me today is Ruchir Jain, a customer support engineer with Cisco TAC, India, with broad experience in routing and switching technologies. He has close to 5 years of experience working with large enterprise as well as service provider networks. He holds a CCI certification in routing and switching and also several Microsoft certification. And interestingly, he has also proclaimed as one of the youngest MCSC in 1999 at the age of 13 years. Welcome, Ruchir.
Thank you, Satish. Nice to be here.
Thank you. Today, Ruchir will talk about possible causes that can lead multicast packet to be software switched, resulting in high CPU problems, systematic approach to be followed when troubleshooting these, a brief summary about tools that would help us isolate these problems very quickly, and finally, we'll dive into some questions handpicked from our community. So with that in mind, Ruchir, can you tell us what are some of the most common common situations in your experience that can lead to high CPU due to multicast?
Definitely, Satish. So let's first look at few of the most common scenarios which we see in the deployment, customer deployments, that result in the traffic to be software switched. So the first thing we'll talk about is Cisco Express Forwarding, CEF. If Cisco Express Forwarding is disabled on your router, then the traffic would have to be software switched. It holds true for both unicast as well as multicast traffic. So we need to make sure that CEF is enabled when you're trying to configure multicast traffic in your network. The next thing that we'll talk about is IP-Igmp join group. We normally use this command when you want to statically join a particular multicast group on an interface. We do not want to rely on the users sending in IP-Igmp joins, but we want to make sure that certain multicast group is always flowing out through a particular interface. When we use IP-Igmp join group, what this command does is, it will definitely send traffic out of the layer 3 interface, but it would also send the traffic to the CPU, resulting in it to go high. The alternative of this command is to use IP-Igmp static group. The difference between static group and join group is, static group will only send traffic out of the layer 3 interface, but will not send to the CPU. So as a good practice, we always prefer to use IP-Igmp static group instead of IP-Igmp join group. The next thing to look at would be reverse path forwarding check, RPF checks. We need to make sure that traffic coming in is coming in on the RPF interface. If it comes on a non-RPF interface, then that traffic is always sent to the CPU. The other thing to look at would be the registration process. If we are using PIM sparse mode, then the first hop router needs to register the source with the rendezvous point. In this process, what we do is, we encapsulate the multicast stream into a unicast stream on the first hop router. Then this particular stream is sent directly to the rendezvous point. This encapsulation of multicast into unicast is not supported in hardware at all, and it is always done in software. So if due to some problem your registration is not getting completed, you would see high CPU on the first hop router as well as on the rendezvous point. So if you see registration happening, we need to troubleshoot it from the PIM perspective, why registration is not getting completed. So far, whatever we have discussed, the problems, they are basically related to the configuration or the network itself. But now let's look at few problems that could be related to the multicast traffic itself. For example, if multicast traffic has a destination IP in the range 224.0.0.x or has a multicast destination IP 224.0.1.39 or 224.0.1.40, then these groups are always switched in software. By default, if you see traffic coming for these groups, it is expected. But if you see a lot of traffic at a very high rate and you think that this traffic is not expected, then it's probably a tag going into your network. Then you need to trace the source of this traffic and try to shut it down. The other thing that could go wrong with traffic would be the TTL value. If we need to route traffic from one router to the other, or from one layer 3 interface to the other layer 3 interface, then we need to make sure that the TTL value is not 1. It should always be more than 1 and should be equivalent to the number of hops that we have, equivalent or more than the number of hops that we have in our network.
Can you give an example where we could see multicast traffic coming with a value of TTL equal to 1?
Sure, Satish. So what we have seen is most of the times there are certain applications that we deploy on our servers, and this application is deployed across several servers, and the communication between these applications on different servers is done via multicast traffic. Now, by default, all these servers are placed in the same VLAN, so we need not route the multicast traffic. So we set the TTL value to 1 on the application itself. This is kind of a security measure as well, so that traffic does not get routed to a different VLAN. But what we have seen is the design in the network change, and customer deploys servers in different VLANs, but they forget to change the TTL value. So what happens is the communication itself is broken between the different VLANs, but the traffic will come into the router, will change the TTL value from 1 to 0, and since the value is becoming 0, we need to send traffic to the CPU for it to be software switched.
Right, thank you.
Okay, moving on. The next thing that could go wrong with the traffic is fragmentation. That is, the packet coming in has a higher MTU which is configured on the egress interface. Normally we see this because the source of the multicast stream is normally your third-party devices like cameras or certain other things that you're using to generate multicast traffic. And most of the times these third-party devices do not generate traffic at 1500 MTU, that is the default MTU of Cisco devices. They generate traffic at a higher MTU value. So what happens is when this traffic comes into a Cisco device, we cannot switch it out of the egress interface due to MTU restrictions. So what we have to do is we have to fragment the packet. Fragmentation for unicast or multicast traffic is always done in software. So we need to make sure that whatever source we are deploying is generating the traffic at right MTU value, and if it is generating at a higher MTU value, we need to make sure that throughout the path of multicast stream in our network, we have the MTU set correctly. Last but not the least are the platform-specific limitations. Each platform has certain limitations with respect to multicast or any other feature that you're trying to configure. So before you start deploying multicast in your network, I would strongly suggest going through the configuration guide to figure out what kind of limitations a platform has.
Can you give a few examples of this?
Definitely, Satish. So let's talk about 7600 and 6500 platform. These platforms have a limitation with respect to the NATing. So let us say your traffic is going out of a particular interface and you have configured NAT on that interface as well. And then on that particular interface, what you're trying to do is change the source IP of the multicast stream. This particular feature is not supported in hardware at all. So it would all the complete flow would be switched in software. Similarly, if I talk about 3560 and 3750 platforms, what we see is the CLI for bidirectional PIM is present, but this feature is not supported in hardware. So you can configure bidirectional PIM and it would be working, but it would always be switched in software.
Okay, thank you.
Okay, moving on. Now let's talk about a systematic troubleshooting approach that we can follow, which can give us a quick resolution to the problem of high CPU. So the first thing that we always want to figure out is what kind of traffic is going to the CPU. Now there are few things that we have at our disposal which we can use to quickly figure out the same. The first thing is, if the platform on which we are seeing the high CPU supports sniffing of the CPU itself, then we can connect a Wireshark or an Ethereal machine to the device and quickly capture the packets that are going to the CPU. However, what we have seen is most of the times when we are troubleshooting, the devices are remotely located and we do not have physical access to them. So it's not an option for us to connect sniffers to the devices and take this kind of captures. In that case, we need to rely on certain other outputs that we can gather, but these outputs are very platform specific. So if I talk about 7600 or 6500 platform, we have a tool called as Nydia Capture. What this tool does is, it's like a cyclic buffer and it's internal to the system itself. So you can run this buffer and it will capture 4096 packets going to the CPU. Then you can dump these packets, analyze them and figure out what kind of traffic is hitting the CPU. Similarly, for 4500 platforms, we have a CPU packet dump utility, which is similar to Nydia, and we can use it to figure out what is going to the CPU. For 3560, 3750 and Metro 3000 platforms, we also have a same kind of utility, but it's not as good as 6500, 7600 or a 4500 platforms. But if we do not have any other option, we can always use this to see what is going to the CPU.
So you have talked about mostly hardware platform, but what about the software platform for like 7200 or 2800?
Yeah, Satish. So basically, these kind of platforms do not have a direct way of seeing what kind of packets are going to the CPU. So it's always a tricky thing to figure out how do we see what is going to the CPU. Though the approach that we can follow in those situations is we'll need to first understand which is the interface through which most of the traffic is coming in. Once we figure out, we can use the command show interface switching to see if the packet coming through that interface is getting hard safe switched or is getting process switched. If we find out an interface on which most of the traffic is getting process switched, what we can do is we can dump the buffers of that interface to see what kind of traffic is going to the CPU. But what happens is, since buffers are cleared very quickly, we might not get all the packets at that time. So it's very hard to figure out what kind of traffic is going to the CPU. But from release 12.2 20T, we have something called as embedded packet capture. It's like an internal capture, sniffer capture inbuilt into the router, which can capture any packet that is coming in or going out of a particular interface. The good thing about this capture is you can actually capture the packets that are going just to the CPU, or you can also capture packets that are getting hardware switched. So if you are running this kind of release, you can always rely on EPC to figure out what is happening.
That's great. Thank you.
Great. The next step would be to analyze the captures that we have taken so far and figure out which problem multicast group is causing the CPU to go high. Now there could be two options. The first thing is you can quickly figure out that it's always a single multicast group that is causing the CPU to go high. In that case, you can select this particular multicast group as the problem group and we can continue with our troubleshooting. But most of the times what we have seen is it's not a single group, and it's, it makes our life a bit hard. So we need to rely on our judgment to select one of the multicast groups out of the several that we see in the captures, and then use this as a problem group and try to fix the problem for this group. Probably if we apply the same solution to the other groups, the problem for them will also get resolved.
So analyzing seems to be a really tough job. So do you use any tools that makes your life easy?
Yeah, definitely. As you rightly pointed out, analyzing is a tough job. So if you do not have the right tools, it might be very cumbersome to figure out what kind of traffic is causing the problem. So it depends on what kind of captures we are trying to analyze. Let us say if you're trying to analyze the sniffer captures itself, which we took using Wireshark or Ethereal, we can always use the filter capabilities of Wireshark or Ethereal, or there are certain graphs that we can make out of those softwares, which can give us a bit of idea what kind of traffic is the problem traffic. But if that capture is not available and we're relying on the captures like Nydia or packet dump utilities, there is no tool to analyze them as such. But if you are good with Linux or Unix, there are commands like grep. You can use them with unique keyword and sort keyword, and that can give you a little bit concise data, and you can use that data to figure out the problem group.
That is GREP?
Yeah, GREP.
Thank you.
Okay, moving on. The next step would be, once you figure out what the problem group is, we'll look at the data part of the problem group to figure out if there's something wrong with the packet itself that is leading it to be software switched. The first thing that we'll check is the TTL value. If it is 1, then definitely it would be switched in software. The other thing we can check is the size of the packet. If the size of the packet exceeds the MTU on the interfaces that we have on the router, definitely we need to fragment the packet, and the packet would be software switched. Similarly, you can check if the destination IP of the packet is in the reserved range, that is 224.0.0.x, or if it's an auto IP group, that is 224.0.1.39 or 224.0.1.40. This would be an expected traffic. But if you see it at a very high bandwidth, then it could be an attack, and we need to figure out which source is sending this traffic, and we need to shut that source down. If you have IP options present also in any unicast or multicast stream, then that traffic would also be software switch. We do not support processing of IP options in hardware.
I remember using a command show IP traffic. So is that still useful in this scenario?
Yeah, so show IP traffic is mostly useful when we are trying to troubleshoot high CPU due to unicast traffic. But it can give us some hints, like if you take that command consecutively after 1 or 2 minutes, you can compare certain fields like the TTL value or the IP option or the fragmentation required. And if those fields are incrementing, then yeah, we can get an idea, okay, why the traffic is going to the CPU. But again, the problem lies that which particular traffic is going to the CPU. So we again need to go back to the captures to figure that out.
Okay, that's great.
Okay, after we have figured out that there is nothing wrong with the traffic and we know what the problem group is, what we could do is we could take the show IPM route, then the problem group output. What this output would tell us are the entries in the software. It will tell us what is the ingress interface, what is the egress interface, what is the current state of the multicast stream, and using this output we can see if there's anything wrong with this output. So the first thing that you need to understand is what kind of PIM flavor you are actually running into your network. Are you running PIM sparse mode, PIM dense mode, PIM bidirectional mode, or source specific multicast? Based on the PIM flavor that you're using, this output would be read differently. So after checking this output, what you can do is you can verify if the ingress interface and the egress interfaces are listed properly in this output. If it is, then you can move on by checking the running config of the egress interfaces to see if IP-Igmp join group is present. If it is, then yeah, as we discussed, the traffic would be software switch. So you need to change this command to IP-Igmp static group. Also, if you see registration flag in the output, then it means that you're running PIM sparse mode and you're trying to register with the rendezvous point. So the router on which you're seeing the high CPU and on which you have taken the command is actually the first hop router on which the source is directly connected.
Could you elaborate more on the registration process, like what could go wrong with the registration process?
Definitely, Satish. So there could be several things that could go wrong with the registration process. So this is the approach that I would follow if I see the registration flag on the first hop router. What I would first check is if my rendezvous point is defined correctly for the multicast stream for which I am receiving the traffic. If it is defined correctly, I'll check if I'm able to reach the rendezvous point. If that is also good, what I'll do is I'll move to the rendezvous point itself. Then I'll check if the S, G entry for the group that, for the source and the group for which we are sending the traffic is present on the RP. If it is present, then it means that I have received the register from the first hop router. If it is not, then there could be a problem with the register message reaching the RP. There might be a black hole in between, maybe an access list denying that traffic, or the other option could be that we do not have the entry for the source in the routing table of rendezvous point. In that case, we will not be able to create the multicast tree and the registration process will not complete.
Right.
After we have verified this and let us say we see the S, G entry on the rendezvous point itself, that means the register message was received successfully. Then what we need to do is we need to move uplink towards the source and see if the multicast tree is broken somewhere. If it is broken, then we'll never receive the multicast stream on the native multicast path, and till that happens, the rendezvous point will never send the register stop message. Okay. When we have verified that our route entry is correct and we do not see any special flags, what we need to do is we need to verify if the RPF is failing. The quick way to verify if RPF is failing is you can do a show IPM route, then the group address, and then the count keyword. With this particular command, you will see the different counters relevant to that particular multicast group. There is a counter called as RPF counter as well. So if RPF is failing for a particular multicast stream, this counter will increment continuously. So if you see that counter incrementing continuously, then you can be sure that RPF is failing and that's why we are sending traffic to the CPU. A quick way to check what is the RPF interface is show IP RPF and then the address for which you want to check the RPF.
So just for refreshing my memory, can you elaborate more on how RPF is done in star.g and s.g entries?
Sure. So if you're trying to check the RPF for a star comma G entry, then in that case the RPF is done using the RP address, the rendezvous point address. So we need to understand that we are learning the rendezvous point, the address of the rendezvous point on the same interface which is supposed to be our RPF interface. So if it is not, then yeah, definitely our RPF will fail. For S, G entry, the RPF check would be done using the source of the multicast stream. So you will use the command show IP RPF, then the source of the multicast stream.
Okay.
Okay. So now if we still are not able to figure out what the problem is and everything looks good so far, then what we need to do is we need to step up our troubleshooting a little bit more. We can use certain debug commands and certain more show commands that will help us figure out what is happening. Most of the times the debug command that we'll use is debug IP PIM, then the group address. This group address is your multicast group address, which is going to the CPU. The other command could be debug IPIGMP join IPIGMP and then the group address. Normally we'll use the second command when we see high CPU on the last hop router, because IGMP is always running on the last hop router. But if it's anywhere else, we'll just use debug IP PIM and then the group address. As you can see that this debug command is specific for a particular multicast group. It will not generate huge amount of output. So it's quite safe to run in production as well. But if you use just the debug IP PIM, it might generate a lot of traffic. So you need to be careful in that aspect. We also have some show commands other than these debug commands, like show IP PIM mapping. This command tells us what is a particular rendezvous point for a particular multicast group. We have the command show IP PIM RPF, which as we discussed will tell us what is the RPF interface for a particular multicast stream. We can also have show IP PIM neighbors to quickly check what are the interfaces on which PIM is enabled and on which we expect the multicast traffic to come in or go out. So in general, if nothing is pointing us what the problem is, we always need to enable debugs, and these debugs will definitely give you a clue on what is the problem. What I'll do is I'll try to put some debug outputs in the working condition, so which in the document and blog which will follow this post, which you can always take debugs in your own situation and check them with the right debugs and see if there's any anomaly. Similarly, I would also be putting all the tools that we have discussed so far, like Nydia Capture, packet dump utilities, and the grep command, an example for the grep command, into the blog and document for your quick reference. Okay, now the other things that we can check, with the multicast stream or the network, if we see high CPU, is that if you're running a layer 3 switch like 6500, 7600, 3750, 3560 or a 4000 switch, and you have disabled IGMP snooping, plus you have a SVI or a switch virtual interface on that particular device for which the VLAN, on the VLAN in which the traffic is coming in, then we will send the traffic to the CPU.
So could you describe why traffic would be sent to CPU?
Yeah, Satish. So we use IGMP snooping to limit traffic to the interfaces which have actually demanded it. It's a layer 2 protocol, so it will work at the layer 2. But if we do not have IGMP snooping, what will happen is the traffic would be sent out to all the ports. If we receive a multicast traffic, we will send that traffic to all the ports of that VLAN. The reason being, we will never learn the multicast address in the MAC address table because it is never the source of the stream. Now what happens is you disable the IGMP snooping, traffic comes in, we'll have to flood that traffic to all the interfaces, and since SVI is considered to be a interface in that VLAN, we'll send the traffic to that interface as well. And the address of the SVI is actually owned by the CPU, so traffic will reach the CPU.
Okay. Right.
Okay. And also there could be several platform specific limitations. So we always suggest that before deploying or designing a multicast solution for your network, you first go through the configuration guide to understand which is a supported feature and which is not a supported feature. Considering that, you would always be deploying something which is a supported one, and basically supported in hardware, not in software. The other thing that could go wrong could be the programming itself, like the Ceph that we have talked so far. If the Ceph entry is corrupted or it's pointing to a wrong value, then traffic will not be switched correctly. It might even point to the CPU, and traffic might go to the CPU, resulting in it to go high.
Okay, so let me take few questions that our users are asking in community. One question that comes often is, how would I know if my device is exceeding the multicast resource in hardware?
Okay, that's a very good question actually. So, what we do is, this is a problem situation that I'll describe to you, which, normally customers come to us. They'll say everything was working fine, and all of a sudden, my CPU is going high. What we do is we do all these captures and analysis, and we see, okay, multicast traffic is cause of your problem. And they'll ask why, because it was working fine earlier. So if we check the logs of the box, and what we would see is we'll see an error message saying that, we are exceeding the hardware entries, and traffic would be software switched now. So that will give you a pointer that we are exceeding the hardware entries. Then you can run some hardware specific commands to the platform on which you are seeing these errors to see how many entries are in use, and if there are any free entries or not. Okay. Based on that, you can take your troubleshooting approach in that direction.
Right. And another question that is, if my multicast stream is jittery, that can be a cause of high CPU?
Yes, it could be. Let us say, you started deploying multicast in your network, and you started to see some kind of jitter in the multicast stream. Multicast, as it being sensitive to delay and jitter, so even if there's a small packet drop or there's a delay in receiving the packet, you will see a jittery stream. Now, the reason could be, let us say you have a long path in your network through which multicast is traveling, and on one particular box, there's some issue because of which traffic is getting software switched. As you know, if our traffic is getting software switched, we'll not switch it at the line rate. So there could be other processes involved, like OSPF, BGP, which can delay processing of the multicast traffic, which can reduce delay or jitter in the packet. So that might break the multicast stream. So definitely, high CPU could be a cause for jittery situations. And if you see, jitter in your multicast stream, what we normally do is we'll check the whole path of the data stream and see if there are any drops, like input queue drops or output drops, or if we see high CPU on any of the platform. That might give us a bit detail on what is the problem.
Thank you. One of our users, Tishi M, he's asking, are ISR routers like 2800 capable of handling good amount of multicast traffic?
I would say no, because it depends upon how much amount of multicast traffic that is coming in. If you're using these routers like 2800 routers for deploying voice solutions or video solutions, even telepresence solutions, then these flows are actually very high bandwidth, and these routers do not support high bandwidth flows in hardware. So it would not be a good idea to use low-end routers for deploying multicast. It all depends actually. If your multicast stream rate is not high, you can use these routers, but if the bandwidth of the multicast flow is huge, then definitely you need to use hardware switch platforms.
Okay, that helps. Thank you. Another question by Jason in the community. He says, is there a different command to enable Cisco Express forwarding for multicast?
By default, if you enable Ceph gets enabled both for unicast or multicast traffic. Maybe in our older versions of the iOS, we had a different command, but sometimes what happens is users ignorantly disable the Ceph for multicast. So the command to enable that would be ipmroute cache on the interface.
Thank you. Thank you, Richard, in fact, for sharing your great insights and presentation. I hope this was really useful for our audience, in troubleshooting multicast.
And you're quite welcome.
Thank you. Hope this tech talk on troubleshooting high CPU due to multicast was useful to you, and we look forward to your feedback. You can send in your feedback using the comment section. You may also ask questions and collaborate via various social media channels like Facebook and Twitter. You can also catch us on YouTube, Google+, and LinkedIn. Goodbye, and thank you for watching.